You've been doing integration for a while now. It's kind of a process you are starting to become more familiar with, and we've been expanding through a whole bunch of different functions to see how it works. And we keep on referring back to differentiation and how they're connected to each other. Okay? Now I know it's really boring, but when you learn terminology and notation, it's really powerful because it lets you describe things and distinguish between different things which are very abstract, which you wouldn't be able to distinguish between otherwise, or describe, really. So before we move on and talk about this, I just want to remember, what are all of these pieces called? They all have names. Okay, there's lots of little pieces here. Okay? So for instance, the left-hand side and the right-hand side each have the whole thing, the whole left-hand side and the whole right-hand side. They each have a name. Does anyone remember? This one starts with an I, and this one starts with a P. Okay, so this is an integral. By the way, in this case, it's not just any kind of integral. It's a definite integral because I actually have boundaries. It could be indefinite if I took them off. What about the right-hand side? It's a primitive. Or a primitive function, really, but you know, everything here, almost everything here is functions, so you kind of get sick of saying it. Okay, that's what the big pieces are. There's a few more specific pieces. You've got this thing, you've got this thing, this thing. What are these called? Let's start with the right-hand side of the easy one. What's that? It's the constant, but it's not just any constant. We're integrating, so it's the constant of integration. Right? Okay, what about this A to B business? It's you can either call it your upper and lower bounds, or as sort of a catch-all phrase, because sometimes, actually, you know, if you go ahead and want to inflict pain onto yourself and do university level maths, you'll learn that you can integrate not just between two values, you can integrate over an entire domain. So you could just say D for domain. So in that case, you wouldn't really call them upper and lower bounds. You would call it, this is more general, a domain of integration. Okay, that's what these are really called. By the way, before I leave off, this sign, the actual sign of integration, what does it symbolize? It's an S, but it's not sigma. Why isn't it sigma? Because sigma was already taken. That's seriously why. But okay, so sigma, which is the Greek letter that we have equivalent to S. Why S? Why not I for integration? Because S looks good. Because a stretched out I would just look weird. The S is short for sum. Yeah? Because integration, like the word integration, it's about taking a whole bunch of little bits and adding them together. You integrate them. You take the sum. Okay? Which is why sigma notation actually has a lot in common to do with integrals. Anyway. What about this guy, the dx? What's it called? What's its relevance? Like if I changed it, for instance, suppose I changed it to a du or a dy or a d theta, what difference would it make?
Well, you can share it with respect to.
Okay, good. So, say that again. It affects what variable I look for when I'm integrating, when I raise powers or when I change the function and so on. Okay? So since it's the variable that I'm looking for, it's called the variable of integration. It's also called a differential, but since we're not differentiating, that name doesn't really make much sense in this context. Okay, now, is one last piece that I'm after. I left it to last because it's the hardest one. That thing, the thing you're integrating, you almost never talk about it. But I'm sure some of you know what it's actually called. It has a name. Does anyone know what's the name of the function that actually gets integrated? Anyone? It starts with an I.
Integral?
Well, we already said that the whole thing is the integral, right? And if I took it on its own, it would not be an integral because I'm not integrating. Just that function, that part of it. Does no one know? No one's ready for it? Are we going to do Heckman for it? No, it'll take too long. I have things to do. We lose a whole lesson because of the assembly, so I'm not going to do it. It's called an integrand? Oh, I knew it, but I didn't say anything because I had no guts. Come on, be brave. It's called an integrand, okay? Now, The reason why I went through that whole lengthy process is not so you could revise your terminology, but when you think about integration and logarithmic functions, okay, there are two broad categories of integrals that will that have some connection to logarithmic functions. Okay, and the two categories are ones where the integrand is a log function, and ones where the integrand is not, but your primitive would be a log function. Okay, let me say that again. There are two broad categories of integration type questions that are related to logs. Okay, the two kinds are ones where the integrand is a log function and the ones where it isn't. Okay, so we'll start with the ones where it isn't, because I think they're actually a bit easier, and they're the ones which you will find on your table of standard integrals. So you could say non-logarithmic integrands. What's going to happen is, up in there, in little f, you're going to have a non-log function, but you'll end up with a log function when you integrate. Okay? So, let's start off. The easy one, the simplest one, a non-log function, you integrate it and you get a log function. What is it? Just the basic one. 1 and x, good. Okay, so that's just the natural log. Okay, no problems. Right? We can extend it a little bit, can't we? Because if you take this idea here, right, 1 over x, we can do simple ones that are very similar to this. For instance, if I were to change it to something like, let's go, let's do that. So I haven't changed all that much. Okay, tell me, what effect does that 3 have? It's just a constant. So in some senses, because it's convenient to me, I can write it out the front. It doesn't really affect the process of integration. Okay? All right, but what about the minus 1? Well, the x minus 1. What's going to happen? How's it going to affect my primitive? Okay, so instead of log of x, I have to have, this is kind of like verse general, isn't it? The x minus 1 has to be preserved on the right-hand side. So I'm going to have log of x minus 1, and that 3 is still hanging about, plus your constant. No problems. Let's have a look at one more, another example, and then we'll generalize it. Okay. What if I had something like, let's go this. Okay. What's going on? Before you actually tell me the answer, what can we do to make the answer a little more clear, a little more obvious to us? What can we do? What are we looking for? We kind of want, in this case, right, what we've got is some function on the bottom and its derivative on the top, right? So, broadly speaking, f dash on f. Okay. I don't have f dash on f here, but I can with a little bit of twisting and turning. What should I do? I should multiply by a half out the front, which will mean I can put a 2 up here, and that's f dash, isn't it? Okay, so I'll do that. A half and 2. Okay? So just like before with that 3 hanging out the front and not really affecting the process of integration. Okay. That half's just going to come out the front, like so. And it's going to be the same thing that we saw before. Okay. Is that alright? Should I fix that? Should I fix it?
Yeah.
Oh my gosh. Okay, now I said we were going to do one more example and then generalize. I've already mentioned it, right? If we have something in the form f dash on f, okay, of which 1 over x is just a very special case where f happens to be just the linear function. If you're integrating that, you're just going to get log of what? Just f, isn't it? Plus your obligatory constant.